Welcome back. We have been discussing superconductivity, in particular BCS theory of superconductivity, and we found out that there is an excitation spectrum with energy E of k, and this is that E of k that we discussed, where we found that it has a gap in the spectrum. So, what is this E of k? Whose spectrum is it? I mean, that is a question one can ask. First of all, these are fermionic excitations, single particle excitations. Secondly, these are actually a very strange mix of both an electron and a hole. These are very special about superconducting ground state, that the excitations above it have a character of both, it is a mixture of both hole and electron. So, it has a character of both hole and electron, and that is interesting because you have now a mixed particle, in the sense that you have mixed holes and electrons to form a new excitation spectrum, and the excitation is gapped, and the gap is delta. The gap is actually 2 delta, spectrum has a gap of delta above 0. So, so this is what this excitation is all about. So this is like, for example, if you had a normal metal like a degenerate Fermi C, then to add an electron you have to give this energy, right, E of k. To add a hole you have to give energy minus k. Here similarly, you have to you want to add a quasiparticle, these new excitations, they are called quasiparticles, these particles which are a mix of holes and electrons. If you want to add, then you have to give this energy. If you want to add at the corresponding to this, then you have to give an energy minus E k. So, this spectrum, for example, if you look at the spectrum, then for example, if E k is far greater than delta k delta, then it will go back to our original spectrum, right, h cross square k square by twice m minus E f naught, which is C of k. The interesting thing is, when it is close to the delta is much larger, and delta and epsilon k is small, delta compared to delta. In that case, you can see that the spectrum is like this. The dashed one is the original fermionic spectrum, which is the metallic conduction band spectrum of the degenerate Fermi gas, whereas these solid lines tell you that the new spectrum of the excitations E of k has a gap. The minimum is this 2 delta, right, and as k becomes larger and larger, epsilon k becomes large compared to delta, then you asymptotically again go back to the original gap, original spectrum. Now, this is like, because what happened is that the particle and hole states hybridized, and they form this new excitation. So, that this original dashed spectrum has now changed to this kind of a spectrum, the solid line. Now, one can actually calculate the density of states of these new excitations, these quasiparticles over the BCS ground state, and that is very simple. What you do is that you use the fact that you do not lose any of the density of states. So, the ds, if I write in terms of ds of E of k is the density of states between E and E plus dk dE, then the number of states must remain the same as the original density of states. So, the density of states is not eaten up, but they can pile up, and that is what we will see immediately, that ds E k by dN E k this is the same as the G that we were writing for free electrons, So, d n of E of epsilon C of k is d C k d E k. Okay. And this is easily calculated, and the two things are done here. One replaces this by its Fermi level value, because that is for all practical purposes in 3 dimensions in particular, this is more or less constant at the, and in 2 dimension of course, the density of states is a constant, and so you can replace this by its Fermi level value, that without any loss of generality. So, all you need to calculate is this one. And so, let us just find out what it is. So, d E k d k d C k is half C k by twice C k by root over E k square C k square plus delta square, right, because E k is root over C k square plus delta square. Now, what you do is that these 2 cancels, and C k you write in terms of E k. So, it has to be entirely written in terms of E k. So, this is E k square minus delta square divided by E of k, and so that means the density of states is just the inverse of that, and that is d of S E k by d n at the Fermi level, which is what you do is equal to E k by root over E k square minus delta square. Okay. Now, for example, you can easily see that this is ill defined, it has to imply that E k has to be greater than equal to delta, and it has to be 0 for E k less than equal to delta. So, at delta it diverges. So, it is delta. So, that is the result that you have from the density of states. How does it look like? Well, it looks you can immediately see how it looks like. It has a huge pile up at minus delta and plus delta, and that means the density of states is like this. D s okay, versus E, and that is the density of states. You have not lost any states, of course, that is how we calculated it, but what you have is that you do not you of course do not have any density of states here, which you had originally, right. You had originally density of states here, whereas now in the gap there are no states. So, those states have all been pushed up or down, and you have this huge pile up of density of states at close to delta. At large distances, of course, it again goes back to the original density of states, large energies. Okay, so this such pile up of density of states has fundamental consequences in superconductivity, and these have been found out, and these are extremely important as far as superconducting ground state is concerned, and particularly their physical properties. Okay. So, let us now go to calculate something which is we had to calculate, and we wanted to calculate right from the beginning, which is the gap. Now that we found that the excitation spectrum has a gap, we need to find it. So, let us just go back to our original calculations. Remember this equation, this is all that you require. These equations were obtained originally, and from that we showed that this is the equation for the gap. So, basically you see that delta will get cancelled from the numerator on the both sides, but then delta remains in the denominator. So, this is like you have to invert this equation to get the delta. So, how does one do it? So, this is how one does it. So, convert this k sum to an integral as we have done so long, and then to a density of states integral, and then replace the density of states by its Fermi level value, which is a trick we have been doing all the time. If a function is so remember, if a function is only if a quantity is a function, the integrand is a function, or the one you are summing is a function only of epsilon k, the non-interacting energies, then you can convert it into a integral involving the density of states. This we have done in the past, and I am sure you know how to do it. So, that is what we are doing. So, this C of k, see there is no explicit k dependence except through C of k. So, you can convert it into a first to an integral, and that integral to the integral over the energy. So, life becomes much simpler, because this is a 3-dimensional integral over k. Now, this is an energy integral, and this is what we did all through. Okay. So, now look at where delta appears. Delta appears in this denominator, right, in this integrand, and so you have to do the integral and then invert this to get the value of delta, and that is exactly what is done. This integral, again remember that V 0 being active only in a narrow energy range above the Fermi level, you can only integrate from 0 to h cross omega dy. Below Fermi level, all states are blocked. So, what you do is you just do this integral, and this is the result. So, remember this is a ground state calculation. So, we are doing this calculation at 0 temperature. These were obtained at 0 temperature, ground for the ground state. Okay. So, here is the result, and now sine hyperbolic inverse h cross omega d by delta is this quantity. So, I just go one more step, write delta equal to h cross omega d by sine hyperbolic of this quantity. Now, again this quantity 1 by V 0 density of states, which is written here as z, we can write it as the original g also, it does not matter. So, this is basically the density of states, and as I said many times, z or g or density of states in the in the normal state can be written as 1 over E f. I mean, it is more or less the ballpark figure is correct. I mean, that is the typical scale of the density of states at the Fermi level, and so this becomes of the order of this. And now you see this is very large. So, and sine hyperbolic has e to the power x plus e to the power minus e to the power minus x, and so out of which you just take the one which is larger, and that means sine e to the power plus x, because this is very large, the argument inside is very large. So, in the denominator then you have h cross omega dy divided by e to the power 1 by V 0 z E f, and that when you convert you will get this. So, this is half, and the 2 goes at the top. So, that is the result that is given here. Now, if you look at this result is very similar to the one we obtained for Cooper problem. So, this is a verification or sort of a justification of Cooper problem even in the many body situation. Remember, Cooper problem was for only 2 particles, that they were blocked by the Fermi sea or Fermi surface was very important in that calculation, and that same argument now leads to a many body ground state, and similar argument, I should not say same, but it is similar argument where the many body ground state was written down, and in that many body ground state we find that there is a gap, which is this, and this gap actually corresponds to breaking a Cooper pair, and that is exactly what we got I mean here as we did in the Cooper problem. So, the physics more or less survives, but the physics is very different in the sense that this is a many body situation. That was just a two particle problem. So, that different distinction you should make. There is another important thing that you should notice here is that this kind of a state, for example, this kind of energy, if you look at it, is not perturbative in V0. V0 being small, one could be tempted to do a perturbation theory, but look at this expression, it has all orders. If I expand it, it will have all orders in 1 by V0, and V0 being small, 1 by V0 is large. So, you should not be able to actually V0 going to 0 limit is ill defined in that expansion. So, if you take any order of expansion, it will not work. So, a perturbation calculation would thus be unable to provide this result. So, that is one important issue you should remember, and that is actually one of the reasons many of the perturbative calculations had failed to account for this theory, the correct theory for the superconductors. Okay. Now, the question is we have to find out what happens above t equal to 0. So, above t equal to 0, there will be some electrons in the normal state, and also some Cooper pairs will start breaking up, and so as temperature increases, the phase, remember this Cooper this wave function that BCS wrote down, as I said, has a fixed phase throughout the entire system, it has a fixed phase. So, and that now starts breaking up, and that is strong phase fluctuation starts, and so the superconducting phase breaks up at some places. So, it fluctuates, and then Cooper pairs are breaking up therefore, and you get these excitations, normal electrons and so on. And what will happen is that if you keep on raising the temperature, at some point this effect will just kill the superconductivity, and that is what Tc is. The value at which superconductivity disappears. What does that mean in terms of this theory? It means delta, the gap, will become 0 at that temperature. So, delta will become a function of temperature, has to become, and delta has to be such a function of temperature that it disappears, becomes 0 at t equal to Tc. And so, let us find that out, and to find that out, what you do is that in that equation for delta, all you do is add the probability of non-occupation of the paired state. So, that is why the factor 2 comes. 1 minus suppose you do not you want to find out the probability of the absence of an electron at a particular energy E at a state epsilon k or C of k, then or any energy E of E, then that will be 1 minus f of E, 1 minus the Fermi function of E. Here it will be 1 minus twice f the Fermi function of this energy E of k, and so that is what you have to multiply this quantity, right. This the only extra piece at finite temperature is this 1 minus 2 f of E at a temperature T, that is all. So, temperature enters in this integrand through the this integral through the Fermi function, and that one has to remember. Now, this part, this 1 minus 2 f E can be written down as a tan hyperbolic quantity, and then again you do the integral. Remember, we are looking now for Tc. Now, at Tc, as I said, delta has to go to 0, that is how Tc is defined, where the gap vanishes. So, in this equation, two things you have done here. One is set delta equal to 0, and the other thing is written this thing 1 minus 2 f whatever in terms of a tan hyperbolic, which is just a simple algebra you can check. Well, that integral is doable, and again the integral goes from 0 to h cross omega d, and the result is known. This is the result is and therefore, this is the temperature where delta was 0, remember. So, this is written as kBTC now, and that kBTC turns out to be 1.14 h cross omega d by e to the power minus again that factor 1 by V 0 ZEF. Okay. So, that means that so the expression the exponential factor remains identical, except that there are numerical factors that change from delta 0. Remember the delta 0 calculation we did, delta at 0 temperature had 2 h cross omega d, and the exponential factor remained the same. So, usually one writes this in terms of a famous quantity, which is 2 delta 0 by kBT, 2 delta at t equal to 0 by kBTC, and that turns out to be this 1.764 into 2 to about 3.52, and that quantity is something that experimentally verified, and that was one of the successes of BCS theory, that immediately they predicted this value of close to 3.5, 2 delta 0 by kBTC. Historically, this 2 delta being the gap, that is why 2 delta by kBTC was the measurement done experimentally, and that turned out to be 3.52, and this exactly is reproduced by this theory. And you can also find out the how delta goes as a function of Tc from this. If you just do this integral keeping the delta, and you could do it, and you will find out that this will be a function of T minus Tc as del. So, it is given. So, this will be a function of 1 minus T minus 1. So, delta T by delta 0. If you do this integral in the previous page, you will find this this relation from here. Okay. If you can do this integral and invert it, then you can find delta as a function of t, and that relation is what I am writing now is 1.74 into 1 minus t by T c to the power half. So, this is the temperature dependence of the energy gap in the BCS theory. So, it is a calculation that can be experimentally now checked, and that was checked of course. So, one can now go ahead and calculate several physical quantities. These quantities like specific heat, for example. For a normal state, we remember that for a normal metal degenerate Fermi gas, the specific heat versus temperature is a linear curve, C goes as gamma t. Okay. Now, what will happen here? Now, we also know that the what does specific heat tell us? Specific heat is a measure of the entropy, right. C by T integral over dt integral over T is a measure of the entropy. So, that means we should be able to find out from the entropy as to what this specific heat is, and we can even guess it. What will happen till Tc? It will be like it will follow the normal state, because at Tc. So, suppose this is Tc. So, at Tc till Tc it is a normal state, normal metal, and then of course, below the Tc there is a gap opening in the spectrum. So, there will be an exponential decay of excitations. So, that means it will get depressed below the usual value, somewhere it has to come down below the usual value, and then but you cannot lose your entropy. So, entropy has to come up and peak somewhere here whatever you lost here should be gained somewhere here. So, this should be the nature of the entropy curve, and this should be exponentially down. It will be minus delta by T or some such thing. I mean, that is a guess one can immediately make. So, let us see what happens. So, this is the calculation that is standard calculation for any fermionic. See, the entropy comes from the excitation. So, you have to excite. When you supply thermal energy, you have to excite, and so the specific entropy has to come from this, and the standard formula for a fermionic system for the entropy is this 2k sum over k 1 minus f k log 1 minus f k plus f k log f k. Okay. This is standard in statistical mechanics. You have done it. If you have not, just check any book in StatMech, you will find this formula. How it is derived is also a straightforward derivation. These are basically non-interacting fermions, and their entropy is this. I mean, there is no other choice. Actually, you will see that this is the only way you can write it off straight away. So, then what you do is that you calculate T ds dt. Okay. So, that is since we prefer to do it in terms of beta, which is 1 by k bt. Okay, fine. So, one calculates this. So, this is the basically this algebra can be easily done. You can do it, and this has two pieces, which is important. This has this piece, first piece, and then there is a second piece. The first piece actually this E k squared term into minus del f del E k gives you the remember that f of k, f has a f is E of k. So, that is what you are using here, because that is the excitation spectrum for the superconductor, for BCS superconductor. So, you take this derivative, you will get up to here. It is straightforward to get here. Now, in the last line, this term, the first term gives you the original original entropy if you do not have a gap. If your gap was 0, that means beyond T c this term, first term will recover your original entropy of the normal state. So, second term is the unusual term, and it describes the effect of temperature dependent gap. So, as I said, the gap had a temperature dependence. So, the second term will reflect this temperature dependence of this gap 1.741 minus T by T c to the power half. So, that gap structure that we wrote down is now coming to play a role in this. So, delta versus T, remember delta T by delta 0 had the structure T by T, right. At T c it goes to 0, and this is the one that is now going to contribute to the second term. So, you can go ahead as delta T goes to 0, which is close to T c. As I said, you can replace E k by the original electronic spectrum, normal state spectrum, and you will get this C E n, which is the normal electronic state as gamma t, which is 2 pi square by 3, the original density of states of the original fermion at the Fermi level times k squared t. So, this was a result we already calculated long back. That is what is reproduced here also, fine. The interesting thing is the second term. Second term is finite below T c and is 0 above T c. So, this will give a discontinuity at T c, right. So, that is the discontinuity one can calculate, and that is one thing that is done here. So, this calculation is very straightforward. df d mod E at T c, they are calculating it at T c. So, delta was set to 0, and then you get this formula, and of course, the d delta square by d beta is there. I mean, that temperature dependence is already there. So, you can do this. This of course, we know how to use this. Derivative of Fermi function is an even function. So, you can just calculate this thing, and this is peaked only around the Fermi level, and then it just gives you n at Fermi level, the density of states at Fermi level, and that is exactly what we did in many other cases. Use this as a delta function, and so all you have to do is now basically calculate this. From here you have to calculate d delta square by dt, and that calculation is simple, and that is what gives this delta c equal to 9.4. In our original notation it is g of E f, here they call it n of 0 k square T c, and this then is delta c by C E n. You can take the ratio is 1.43, and this can be checked, and this is what is checked experimentally. So, let me show you the experimental result. Look at the entropy. As I said, entropy has to drop below the this free electron entropy, and specific heat of course has this jump here. So, whatever you lose here you have to gain here, and that is what I mean, if you lose it you have to gain it somewhere. The entropy cannot be cannot just vanish, and so this is the okay. So, the way one sees it, that this part, the part below the normal specific heat comes from the fact that there is a gap. So, that gap reflects in this entropy going exponentially up at low temperatures, and then it goes above the normal state at finite at some temperature, and then you basically have a jump at this point in the entropy. So, the entropy of course has to go to 0 at 0 temperature. So, that happens in both cases. So, that is not a problem. Specific heat has this exponential behavior below the below this as I said, the below the because there is a gap, it has this so it comes down below the normal state as a function of temperature, and that had to happen because there is a gap in the spectrum. Okay. So, so the idea is that since you have a gap, you have to excite the quasiparticles across the gap, and that has a temperature dependence, and that gives rise to this coming down of the specific heat as a function of temperature. So, in the next class what we will do is we will discuss electron tunneling, and that is for the next class, and that is another experiment that one does to find out the verification for superconductivity theory of superconductivity, BCS theory of superconductivity.